August 1943. A remote airfield in occupied France controlled by the German Luftwaffe. Shortly after 1600 hours, Oberleutnant Werner Schulz, Chief Technical Officer of Jagdgeschwader 26, received notification that would define his understanding of the air war. An American Republic P-47 Thunderbolt had been forced down during combat operations. The pilot was in custody. The aircraft remained largely intact. For German technical intelligence, this represented a critical opportunity. Since early 1943, Luftwaffe pilots had filed combat reports describing an American fighter with performance characteristics that challenged existing assessments. The aircraft demonstrated high-altitude capability, exceptional durability under fire, and firepower density that exceeded German designs. Now, for the first time, German engineers would conduct a systematic examination. Schulz was not a combat pilot. His background was aeronautical engineering. Before the war, he had worked for Messerschmitt AG, contributing to development programs for the Bf 109. His assignment to Jagdgeschwader 26 placed him in the technical intelligence section, where his role involved evaluating captured enemy equipment, identifying vulnerabilities, and recommending tactical countermeasures to exploit those vulnerabilities. When Schulz arrived at the airfield and observed the P-47 on the parking apron, his initial reaction mirrored that of most German pilots. The aircraft appeared grotesquely disproportioned. The fuselage was massive, built around an enormous radial engine. The overall configuration seemed fundamentally wrong. German pilots had nicknamed it Die fliegende Milchflasche, the flying milk bottle. The designation was not affectionate. The P-47 weighed nearly 8 metric tons at maximum loaded weight. By comparison, the Focke-Wulf FW-190, Germany's primary frontline fighter in the West, weighed approximately 4 metric tons. The visual disparity was striking. Looking at the P-47 stationary on the tarmac, Schulz understood the pilot's skepticism. It looked like an aircraft that defied basic aerodynamic principles. But Schulz approached the examination methodically. Appearance was irrelevant. Performance data was what mattered. As he began his systematic assessment, what he discovered would fundamentally alter his understanding of the strategic situation. If you appreciate detailed evidence-based World War II history, please like this video and subscribe to the channel. Comment below and let us know where you're watching from. Schulz began with the power plant, the Pratt & Whitney R2800 double Wasp radial engine. When his technical team removed the engine cowling, they paused. The engine was enormous. 18 cylinders arranged in 2 rows of 9, creating the distinctive radial configuration that explained the P-47's bulky frontal profile. But size alone was not what arrested Schulz's attention. It was the manufacturing quality and engineering sophistication. Every component was machined to tolerances that German factories were increasingly struggling to maintain under wartime conditions. The cylinders were uniform and perfectly balanced. The crankshaft demonstrated metallurgical quality that suggested access to high-grade alloys without material shortages. Schulz documented his observations. Based on engine displacement and design characteristics, this power plant was producing at least 2,000 horsepower, possibly more when operating with the turbo supercharger system integrated into the aircraft's fuselage. For context, the BMW 801D radial engine that powered the FW-190 produced approximately 1,700 horsepower at maximum output. That represented the absolute limit of German radial engine technology in 1943. The Americans were mass-producing engines with 20 to 30% more power output, and critically, they were doing so without apparent difficulty. This was not a prototype or experimental engine. This was a production unit, one of thousands. Schulz examined the engine's construction for evidence of shortage accommodations, the kinds of compromises German factories were being forced to make. Lower-grade materials, simplified manufacturing processes, anything to conserve resources. He found none. The engine was constructed with high-grade aluminum alloys, precision bearings, and components that showed no evidence of material constraints or manufacturing shortcuts. It was built correctly, not expeditiously. One of Schulz's assistants, a mechanic with years of experience on German aircraft, pointed to the cylinder arrangement. "Herr Oberleutnant, each cylinder is individually removable. If one is damaged, you can replace just that component without disassembling the entire engine." Schulz nodded. The design was brilliant from a maintenance perspective. It meant faster repairs, reduced downtime, more aircraft operationally available. German engines required extensive disassembly for major component repairs. This American design assumed that maintenance would occur frequently in field conditions and needed to be efficient. It was a design philosophy that prioritized operational availability. But what captured Schulz's attention most intensely was the turbo supercharger system. He had reviewed intelligence reports describing this technology, but examining it directly was different. A complex network of ducting ran from the engine down through the fuselage to a turbine mounted in the rear section of the aircraft. The system used exhaust gases from the engine to spin a compressor at over 20,000 revolutions per minute, forcing pressurized air back into the engine. The engineering complexity was extraordinary. Exhaust had to be channeled through ducting capable of withstanding extreme temperatures. The turbine had to spin at speeds that would destroy inferior bearings. The entire system required precise calibration to avoid damaging the engine through overpressurization. German engineers had experimented with turbo supercharger technology. Daimler-Benz had conducted development work. Junkers had explored applications for bomber aircraft, but Germany had never successfully fielded a functional turbo supercharger system in operational fighters. The technical challenges were too significant, materials were too difficult to source, manufacturing was too complex for wartime production constraints. Yet here it was in an American fighter that was being mass-produced. Not a prototype, not an experimental aircraft limited to specialized units. A production model, one of hundreds or thousands already operational. Schulz performed the calculations. With this turbo supercharger, the P-47's engine could maintain full power output at altitudes where German fighters lost performance. Above 25,000 feet, the FW-190 and Bf-109 experienced significant power reduction as their mechanical superchargers struggled in thin air. The P-47 would be hitting optimal performance, fast, powerful, and completely dominant in the high-altitude environment where German fighters had to operate to intercept American bomber formations. His assistant asked the obvious question, "Can we replicate this system, Herr Oberleutnant?" Schulz shook his head. "Not with our current manufacturing capacity. This system requires precision machining, high-grade steel alloys, and thousands of man-hours of skilled labor. We are already struggling to produce sufficient basic aircraft. Adding this level of complexity," he paused, "it exceeds our capabilities." The realization was stark. The Americans had not simply built a superior fighter. They had built a fighter that represented a level of industrial sophistication Germany could not match with available resources. After completing the engine examination, Schulz turned to the airframe itself. What he discovered was equally significant. The captured P-47 had sustained considerable battle damage. Cannon shells had torn through sections of the fuselage. Machine gun fire had riddled the wing structures. Yet the aircraft had flown back to friendly territory and executed a controlled landing. Schulz examined the damage patterns carefully. Multiple 20mm cannon hits, the type that would typically destroy a German fighter. But the P-47 structure had absorbed the impacts. The heavy-gauge aluminum skin, the robust internal framing, the redundant control systems, all contributed to exceptional durability. He reviewed damage reports from Luftwaffe units. Repeatedly, pilots reported firing cannon rounds into P-47s and watching the American fighters continue flying. The reason was now evident. The P-47 was constructed like an armored vehicle. Where German fighters were optimized for weight reduction and maneuverability, the P-47 was designed to absorb battle damage and remain operational. The cockpit armor was extensive. Thick steel plates protected the pilot from multiple angles. The windscreen was armored glass, far thicker than anything installed in German fighters. But most significantly, the R2800 radial engine served as a massive protective shield. Unlike the liquid-cooled inline engines in the Bf-109 and FW-190, the radial engine had no vulnerable coolant system. You could destroy cylinders, and the engine would continue running. Schulz found documentation showing that P-47s had returned to base with multiple cylinders destroyed, fuel tanks punctured, and control surfaces severely damaged. German fighters with equivalent damage would have been lost. One of his engineers made an observation. "It is over-engineered. They have added weight for durability that could have been used for performance enhancement." Schulz nodded. "Yes, but they can afford to. They have engines powerful enough to carry the additional weight. We do not. We must optimize for weight because we lack the engine power to overcome it." It was a fundamental difference in design philosophy. Germany built aircraft at the edge of technical possibility, extracting every ounce of performance from limited resources. America built aircraft with massive safety margins, compensating for any inefficiencies with brute force power. And the American approach was proving more effective in operational conditions. Schulz examined the P-47's armament next. 8 Browning M2 50 caliber machine guns, 4 mounted in each wing. His assessment of the implications was immediate and concerning. Each gun had approximately 400 rounds of ammunition. Total ammunition load, 3,200 rounds. Combined rate of fire for all 8 guns, over 100 rounds per second. The firepower density was devastating. A 1-second burst would deliver 100 heavy projectiles into the target area. A 2-second burst, typical for a firing pass, would launch 200 rounds. German fighters typically carried 2 or 4 machine guns plus 1 or 2 cannon. Total firepower was less, and ammunition was more limited. A Bf-109G might have 60 rounds for its MG-151-20 cannon and 500 rounds for its MG-131 machine guns. Once that was expended, the pilot had to return to base. The P-47 pilot could fire almost continuously for 30 seconds, enabling multiple long bursts across several combat engagements before ammunition depletion. But it was not just quantity. Schulz examined the 50 caliber rounds themselves. They were heavy, high-velocity projectiles capable of penetrating armor and structural components with relative ease. He had reviewed pilot reports describing the effect of P-47 fire as a wall of lead. Now he understood the description's accuracy. With 8 guns converging at a focal point, anything caught in that cone of fire would be shredded. German aircraft, with their lightweight construction and limited armor protection, would disintegrate under this firepower. A P-47 did not need precision. It needed to get the target generally forward of the aircraft and pull the trigger. As Schulz compiled his technical report, he began to recognize a pattern that transcended any single component. Every system on the P-47 indicated an underlying industrial capacity that was extraordinary. The engine required precision machining and high-grade alloys. The turbo supercharger required advanced metallurgy and complex manufacturing. The airframe required massive amounts of aluminum. The armament required a functioning ammunition production industry. Any one of these components would strain German industry. The P-47 had all of them integrated into a single aircraft and was being mass-produced. Schulz requested production data from intelligence sources. What he learned was profoundly disturbing. Republic Aviation was building P-47s at a rate that seemed impossible by German standards. By late 1943, they were producing over 500 aircraft per month. Plans called for ramping up to 600, 700, even 800 per month by 1944. For comparison, German factories were struggling to produce 300 to 400 single-engine fighters per month total across all types. And German production was constantly disrupted by Allied bombing campaigns targeting manufacturing facilities. But the figures became more alarming. The R-2800 engine was not exclusive to the P-47. It powered multiple American aircraft types. Total production of R-2800 engines would exceed 125,000 units during the war. Over 125,000 of these 2,000 horsepower engines. Germany's entire production of aircraft engines for all types across the entire war would be roughly 250,000 units, most of them significantly less powerful. The Americans were building more of a single advanced engine type than Germany could produce total engines. The disparity was incomprehensible by any reasonable metric. Schulz sat at his desk, staring at the numbers. He recalculated, thinking he must have made an error, but the numbers remained unchanged. American aircraft production for 1943 was projected to exceed 85,000 aircraft. German production would be approximately 25,000, a ratio of more than 3 to 1. But it was worse than a simple numerical comparison because American aircraft were on average heavier and more complex. A single B-17 bomber required more aluminum and man-hours than 3 Bf-109 fighters. The Americans were building thousands of B-17s. The material disparity was overwhelming. America was fighting a global war, supplying the Soviet Union with thousands of aircraft and tanks, equipping British forces, and still outproducing Germany in every category. Schulz's final report was scheduled to be presented to High Command in Berlin. As he compiled his findings, he knew he was writing something potentially dangerous. The report documented the P-47's technical superiority in multiple areas. It acknowledged that Germany lacked the industrial capacity to produce equivalent systems, and it contained a conclusion that would be viewed as defeatist. His summary read, "The P-47 Thunderbolt represents a level of industrial and technological sophistication that exceeds Germany's current capabilities. Its widespread deployment suggests American production capacity far exceeds previous intelligence estimates. Recommendation: tactical adjustments to minimize engagement with P-47 at high altitude. Strategic assessment: continued attrition against numerically and technically superior enemy aircraft will result in unsustainable losses." In other words, we cannot defeat this, and if we continue fighting the same way, we will be destroyed. Schulz's commanding officer reviewed the report and looked at him with a mixture of respect and concern. "You know this will not be well received in Berlin. They do not want to hear that American aircraft are superior." "Should I alter the findings?" Schulz asked, already knowing the answer. "No. The report is accurate, but prepare yourself. The leadership does not respond well to uncomfortable truths." The report was forwarded up the chain of command. Schulz never received an official response, but he heard through informal channels that it had been dismissed as overly pessimistic. One staff officer reportedly said, "This engineer has been demoralized by enemy propaganda. The P-47 is crude American engineering, inferior to our designs." Schulz was not surprised. He had observed this pattern before. Intelligence that contradicted Nazi ideology was rejected regardless of its accuracy. In the months following his report, Schulz watched his predictions materialize. P-47s appeared in increasing numbers over Europe. German fighter losses mounted. Experienced pilots were shot down and not replaced. The tactical recommendations he had made, avoiding high-altitude engagements using hit-and-run tactics, were slowly adopted. But by then, it was too late. The Americans had achieved air superiority through sheer weight of numbers and technical advantage. Schulz examined other captured American aircraft. Each one told the same story: superior materials, sophisticated systems, evidence of an industrial base operating at a scale Germany could not match. He examined a captured C-47 transport aircraft. It was one of over 10,000 that would be produced. Germany's entire transport fleet consisted of a few hundred aircraft, mostly obsolete designs. He examined a P-51 Mustang. It combined the range of the P-47 with even better performance characteristics. The engine was a Packard-built Rolls-Royce Merlin, produced under license in America. Thousands of them. Every aircraft he examined reinforced the same conclusion. Germany was losing an industrial war to an enemy with overwhelming material superiority. What haunted Schulz was that this information was available. The intelligence existed. German agents were reporting on American production capacity. Captured equipment proved the quality, but the leadership refused to accept it. Or more accurately, they accepted it, but believed that German will and superior tactics could overcome material disadvantage. Schulz had been trained as an engineer. He believed in numbers, in mathematics, in physical reality, and the physical reality was undeniable. Germany was being buried under an avalanche of American steel. After the war, when production figures were declassified, Schulz's estimates were proven conservative. He had actually underestimated American capacity. Total American aircraft production from 1940 to 1945, over 300,000 aircraft. German production in the same period, approximately 94,000. the United States produced over 5,600 P-47 Thunderbolts alone, more than Germany produced Bf-109s and FW-190s combined. The R-2800 engine that Schulz had examined with such concern in 1943, over 125,000 were built, not just by Pratt and Whitney, but by Ford Motor Company, Chevrolet, and other automotive companies converted to war production. The industrial mobilization that produced these numbers was unprecedented in human history. American factories that had been manufacturing automobiles were retooled to make aircraft engines. Shipyards that built freighters were building aircraft carriers. And it was not just quantity, the quality remained high. Late-war American aircraft showed no signs of declining standards, no shortcuts, no compromises forced by material shortages. German aircraft, by contrast, showed increasing evidence of resource constraints. Lower-grade materials, simplified construction, quality control issues as experienced workers were drafted and replaced by forced labor. Schulz survived the war and was interrogated by American technical intelligence officers. They were particularly interested in his 1943 report on the P-47. "Did you really conclude from examining one aircraft that Germany would lose the war?" an American officer asked. Schulz thought for a moment before answering. "I concluded that Germany could not win an industrial war against America. The P-47 was evidence of a production capacity we could not match. Every component, every system required resources and manufacturing capability that exceeded Germany's total capacity. But you were just one engineer. Surely others reached the same conclusion." Many did. But in the Third Reich, stating inconvenient truths was dangerous. Better to remain silent than to be accused of defeatism. The American officer nodded. "We found your report in captured German files. It was marked, filed, no action required. Did that surprise you?" Schulz laughed bitterly. "No, I expected it. The Nazi leadership did not want intelligence, they wanted validation of what they already believed. When reality contradicted ideology, reality was dismissed." The story of Werner Schulz and the captured P-47 is a microcosm of Germany's strategic failure. A trained engineer examined enemy equipment, reached an accurate conclusion about Germany's industrial disadvantage, and was ignored. His experience paralleled that of Admiral Wilhelm Canaris, who warned about American industrial capacity. Albert Speer, who knew Germany could not win a production war. Adolf Galland, who recognized the P-47's tactical superiority. Sepp Dietrich, who knew the Ardennes offensive would fail for lack of fuel. In every case, competent men saw the truth and were trapped in a system where truth was subordinate to ideology. They provided accurate assessments and were dismissed as defeatists or pessimists. The Nazi regime was built on the premise that German racial and cultural superiority would overcome any material disadvantage. That will and determination mattered more than industrial capacity. That ideology could defeat mathematics. They were wrong. And men like Schulz knew they were wrong from the moment they examined the evidence. But knowing the truth and being able to act on it are different things. Schulz's report on the P-47 should have been a strategic warning. It should have triggered a fundamental reassessment of Germany's strategic position. Instead, it was filed away and forgotten. The P-47 went on to become one of the most produced fighters of World War II. Over 15,600 were built. They destroyed thousands of German aircraft. They supported the invasion of Europe. They helped achieve air superiority that made Germany's defeat inevitable. And it all started with one engineer examining one captured aircraft and realizing that his nation had already lost a war they did not know they were fighting. Not a war of soldiers or tactics, but a war of factories and resources. A war where the side with more oil, more aluminum, more steel, and more industrial capacity would inevitably win. America had all of those things in abundance. Germany had none of them. The P-47 Thunderbolt was not just an aircraft. It was physical proof of an industrial reality that could not be overcome by ideology or willpower. Schulz recognized this in August 1943. The German leadership did not. That difference determined the outcome of the war.